To introduce myself, my name is Ian Trevoranis. I am the Product Line Manager for HORIBA Particle Products here in the Americas. I'm going to be speaking to you today for hopefully roughly 45 minutes about how you might interpret your laser diffraction particle size results. It's a very wordy title, and there's certainly a lot of different things we can do here, but I'm just going to touch briefly on a few topics. More information is, of course, always available at our website, horiba.com/us/particle, right here. So the outline for today's presentation is we're going to cover what I call the basics up front, and that's just to get everyone on the same page. And this presentation is really best for people that maybe have lost a little bit of confidence in how they can understand what they're seeing in their results, or people who are brand new to laser diffraction. After we cover the basics, I'm going to define some parameters, just so that you know what certain names mean. I'm going to cover some guidelines on how we recommend you choose parameters, maybe for a specification. And then we're going to very briefly interpret some generic results. I think I call it advanced interpretation. It's not terribly advanced, it's just some case studies, essentially. So here's the workflow. You have some particle size analyzer, maybe the HORIBA LA950. You have some material. And then you have yourself, or actually this is what my wife thinks I'm like in the lab. And then you have some particle size distribution result. So analyzer plus sample plus U equals some graph. Now the problem is, who knows what the heck this graph is telling you, right? If you're brand new to the technology, brand new to the analyzer, brand new, frankly, to particle size, because how many of us learned that when we were going through school? It's just going to look like a big question mark. So here are the basics. We have a particle. And the particle is very likely not going to be a sphere. It's going to be one of a distribution of particles. So this is really what most of real-world samples look like. Many different shapes, many different sizes. And what that leads to is what we call a particle size distribution. If you were going to ask me, what's the particle size of my sample, really, to me, that just means you're asking for a single particle size. So I could give you a single number, like 4 microns. But because there's a whole distribution of sizes and shapes of particles in your sample, the analyzer isn't going to give you just one number. It's going to give you a whole heck of a lot of numbers. We call this the particle size distribution. It's typically a fairly complex-looking graph, although in some situations they can be very simple, narrow, Gaussian graphs. So a historic challenge with particle size analysis is to define what the most meaningful size of your particle is. Right? So again, if it's not a sphere, you really have some choices to make or some additional understanding. So if you were again to ask me, what's the size of this particle? I could say, well, it could be a size like a width. It could be a size like the length, or we could try drawing some diagonal through the particle. And they're all valid ways of describing the particle size. And what we really need to know is, when we run it through a particle size analyzer, any technology, any manufacturer, what size definition is that analyzer actually reporting to us? And here's one of the key takeaways I hope you get from today's presentation, which is different size definitions lead to different results. Right? And this is especially true when comparing different technologies. I'm going to focus most on laser diffraction as a technology for today's presentation, but there's a huge range of different technologies out there in the world, some more common than others, and most of them look at different aspects of the particles, which means that they're going to report different size definitions, which means they're going to report different size results. So what sizes can be measured? Many different technologies will take a real-world particle with all sorts of different size definitions and basically compress it into a sphere or a circle, because it's easy to solve a lot of the complex mathematics that you need in order to get particle size from the raw data. It's really only easy to solve when it's a simple case like a sphere or a circle. So you'll see a lot of techniques, especially light scattering techniques, make this assumption that whatever particles are in your sample are actually spheres. And there's going to be some error built into that assumption, but a lot of times it's error that we can live with because it still shows changes in product performance or process performance. For example, we have laser diffraction. Again, what I'm going to be focusing on today. Laser diffraction reports what's called the equivalent spherical diameter. And again, that's just what I talked about. Regardless of what the particle shape may be, it's going to show you what the equivalent sphere would be. So a median size of 10 microns is really saying the median size of this particle distribution if they were all spheres. Dynamic light scattering is another very popular technology, mostly meant to look at very small particles less than 1 micron. That also gives us a spherical diameter, except we're calling it the hydrodynamic radius, because really what it's doing is it's reporting some diameter of the particle and then really some surrounding layer of fluid or something else around it. I won't get too deep into the explanation of what the hydrodynamic radius is. Just know that it's not the actual surface of the particle. It's the surface plus some surrounding layer. There's all sorts of different ways to perform image analysis. There, in fact, are several ways of performing it just in our lab here. And one of the advantages of image analysis, where you're actually taking images of the particles, is that you can draw your lines any number of different ways you want to describe the size of the particles. So with an image analyzer, you can describe lengths, widths, even equivalent spherical diameters if you needed to compare to a different technique. A fourth technique is acoustic spectroscopy. This also, for the sake of simplifying some of the math, reports equivalent spherical diameter. So let's go into a little bit more detail about laser diffraction. It assumes that the particles you're looking at are hard and spherical. And what I mean by hard is essentially non-porous. Right? It doesn't look like an asteroid. It basically looks like a hard rubber ball, something like that. And this is what a typical distribution might look like. Where the y-axis, at least in the case of the LA950, we define as Q%, which is the amount of each size by volume, and the y-axis, which is sizes on a log scale, and it always goes from small to large. Dynamic light scattering, similar in a lot of ways. It also assumes a hard spherical shape. We don't call it Q% for I guess reasons of style. We call it frequency percent. It's the same thing, just the amount of each size. In this case, it's one of these graphs is by volume. The red graph is by volume. The blue graph is by scattering intensity. But that's something for another webinar. And the x-axis is also an increasing logarithmic size. Image analysis measures the particle projection, so literally shadows on a screen. It doesn't make any assumption by shape, or if it does, it's minor, and nothing as extravagant as assuming everything's a hard sphere. And the advantage is, of course, that depending on how you define the size parameters you want to look at, you can get a little bit more accurate data. This distribution is actually showing us another piece of data, which is called the undersize curve. It could also be called percent passing or big Q3. This is something that is probably familiar with a lot of sieving people in the audience today. Again, acoustic spectroscopy also assumes a hard spherical shape, and also the distribution looks very similar as we've seen before. So a quick poll question, and the question I have for you is, do you have non-spherical particles, or do you even know? A lot of times users don't know what shape their particles are in. And just real quickly, if you don't mind, go ahead and type that into the question box. So Leon is saying that he uses irregular particles. Several of you know that the particles are irregular. That's good. And in the next few slides, or in the next few minutes, I should say, we're going to cover some terms to describe the irregular particles. Doug is saying his particles are absolutely non-spherical, crushed rocks. Yeah, very difficult to get spheres out of any kind of grinding mechanism. All right. Ah, uh, Milda or Mita is saying that they assume that their particles are round. That's very interesting. And whenever we get sample submissions into our lab here in Irvine, I never ask my chemists to assume anything about the sample. So, it takes probably a few minutes if you have access to an optical microscope just to pop them underneath an objective onto a slide and just get a quick idea of, how spherical are they, how non-spherical are they, right? If they are very close to being round or spherical, then the amount of error introduced in your laser diffraction measurement is going to be much smaller. If they look like needles, then the error is going to be much more substantial. All right, thanks everyone. So some conclusions from this section. Understand your data, and you don't have to be an expert in the data, but a little bit of understanding goes a very long way. I would ask that try and find something out about the particles in your sample. Just like I was describing, I asked from the chemists in our applications lab. Right? It doesn't take that much effort, and it could be useful, may not be useful, but 5 minutes of effort could tell you something very interesting. And particles have multiple dimensions, and it may not necessarily be important to know every single dimension of your particles, but know which dimension your analyzer or analyzers measure. If you have something that looks like a needle and is large enough to be measured by image analysis, there may be an advantage for you to measure it with an image analyzer as opposed to a light scattering technique, which assumes that everything has to be a sphere. So that was the basics. Now we're going to go forward and define some parameters. And a lot of slides in this section, I'll just say, are for your reference. I'm not going to spend time reading the entire slide. One critical distinction is that in the LA950, or any laser diffraction instrument, we really talk about volume-based diameters. So you can represent the particle size distribution on a number of different bases. By default, laser diffraction instruments report on a volume base, which means the size, a median of 10 microns, is a particle that has a volume where the equivalent, I'm sorry, a volume basis is particles that have some volume where if you take the diameter across the sphere, it's 10 microns. I won't get too deep into it. Just know that a volume basis will give you different results than a surface area basis or a number basis. Some more terms, different ways of describing the y-axis on a lot of graphs. Again, volume-based diameter, cumulative percent on diameter, diameter on cumulative percent, or we usually see these in different specifications from users. And now a bunch of terms to describe the shape of different particles. So acicular is the formal way of saying needle-shaped. They have to be rigid. If they're non-rigid, but kind of needle-shaped, we would call that fibrous. Different ways of describing shape measurements or shape parameters, instead of just naming the shape, are aspect ratio, sphericity, roundness. There's actually tons and tons of different parameters here. I'm just naming 3 of the most common. So, second poll question. How would you describe your particle shape? So earlier we talked a little bit about irregular particles. I'll put some of the other definitions back up on the screen. And if you go to your chat box, do you have new terms that you could use now? Is it, instead of being irregular, are they angular now? Maybe a little bit hard angles, sort of like an abrasive particle. Maybe are they acicular, needle-shaped? Granular, good. And a few minutes ago I was talking about different error that's introduced into the measurement, and that's just a function of the technique, right? It has nothing to do with manufacturers or different model versions or anything like that. But granular, blocky particles are probably the next best thing after spherical because they're a compact shape. The aspect ratio tends to be very close to that of a sphere, or at least much more close than a needle. So that's the next best things in terms of error. And when I talk about error, I'm only really talking in terms of accuracy, not in terms of precision or reproducibility, or even the ability to spot trends of increasing or decreasing particle size. All right, we'll move along. Thanks again for giving me some interesting information. Now let's define some size terminology. So most of the time, when we're talking about laser diffraction, we're talking in terms of microns. So the LA950, for instance, can measure down to 10 nanometers. It can measure small, fine tails down to 10 nanometers. It can measure medians down to 30 nanometers, and it can measure medians up to about 2,900 microns, or 2.9 millimeters, with tails going up to 3 millimeters. But a lot of the applications we traditionally see for laser diffraction are in the micron range. We could also call it micrometers, but micron's a little bit faster and easier on the tongue. When we talk about very small particles, anything less than 1 micron, we're typically talking about nanoparticles in the nanometer range. We could also call them colloids or macromolecules, depending on application in our training. And these is an area that's typically, if it's so small that it's beyond the size detection limit of the LA950, typically we're looking at these particles using ultramicroscopes or by dynamic light scattering. And there's other techniques, but these tend to be the two most common. Just a quick graph that shows relative size. It just occurred to me I may have been speaking over the slide transition a little bit, so I'm going to try and slow that down. So if you were to take a hair off your head and sort of get a cross-section of it and blow it up to this size, this would be the sort of relative size of other things, right? So dust particles, not all dust particles are at 10 microns, but that's an easy gauge. So dust tends to be less than 1/10 of the size of a strand of human hair. Unfortunately, I'm starting to lose mine, so and it's thinning, so I don't think mine is 150 microns anymore. I'm glad I can't measure it. I'm sure that wouldn't be a happy thought before Christmas. But we can get even down here to the point where on the same scale we can't even look at the size of the dot. It's so small. And that'll be proteins, viruses, macromolecules, very, very small things, colloidal golds, very small particles. Next poll question. Which size ranges do your samples cover? Do you tend to be in the nano range, in the micro range, or even larger, millimeters? A lot of people in the micro range. That's good. You're in the right presentation. Because we're focusing on laser diffraction, we want very few people to be larger than a millimeter, because you're probably watching the wrong technology. A lot of people in the micron, a few people in the nano, and that's really one of the major developments in laser diffraction technology over the last, let's say, 8 to 10 years, is the ability to extend the lower size limit for detection. So the LA950, to date, as far as I know, is still the laser diffraction instrument which can measure the smallest particles. So I was saying earlier we can measure medians down to 30 nanometers. That's historically extremely small for this technology, and it really is very far into the range of dynamic light scattering. So the upshot is we do see a lot more applications now which are strictly in the nanoscale range. So again, thank you for sharing some information. Return to the presentation. So now we're going to talk a little bit about defining central values. And by central values, the three most common that I mean are mean, and that's no pun intended, mean, median, and mode. And we'll start in reverse order. The mode is simply the most common particle size. It's the very top of your distribution, the peak of your distribution. The median is the 50% point. 50% of your particles on that size are going to be smaller, 50% are going to be larger. And the mean actually has many, many definitions, which we'll get into in just a second. You can think of it as a weighted average or the center of gravity. If you were to put the distribution and try and balance it on your finger, you'd have to find the mean, and that's where you'd be able to balance it. So as I just said, we're going to discuss a little bit about how we can define the mean. A lot of times you'll just think of mean in terms of arithmetic, which is what we all learned at school, right? If you have 3 spheres of diameters 1, 2, and 3, we think in terms of average. All right, so the average size of the set of 3 spheres is 1 plus 2 plus 3 divided by 3, which is 2. This is actually called the number mean, or the D10. This is not the mean that's reported by the LA950 or any other laser diffraction instrument. We can get that number out, but by default, we don't show this number. Instead, the number that the 950 shows by default is the volume-based mean, or the D43, down here at the bottom of the slide. And on the slide, you see 5 different ways, and there are many more than this, trust me, but this slide has 5 different ways of calculating a mean value. And none of them are wrong. They've all just been calculated using different techniques. For instance, the D32 here, which is also known as the Sauter mean diameter, SMD, is used for different technologies. It's used to give you different information. Now the reason laser diffraction uses the D43, the volume-based mean by default, is because by default laser diffraction is a volume-based technique. All of the results are being reported on a volume basis. Now, another valuable thing of reporting the volume-based mean, as I transition to the next slide, another valuable thing is that the D43 emphasizes the detection of large particles, which makes a little bit of sense based on how it's calculated. So we call it the 4-3 because the numerator, the diameters of different particles are being raised to the 4th power, and in the denominator, those same diameters are only being raised to the 3rd power. So large particles raised to the 4th power, that ratio is going to be much larger than small particles raised to the 4th power. So D43 emphasizes the detection of large particles, which makes it very valuable when you're monitoring a grinding operation or when you want to make sure that no large particles or a controllable amount of large particles are in your distribution. Now, even if that's not interesting to your application, one of the takeaways I hope you get from today's presentation is that looking at the D43, the default mean value out of laser diffraction instruments, will always emphasize the detection of large particles. That's the takeaway from this slide. Now, going back to central values, the first slide a few back showed a Gaussian distribution, a symmetric distribution. If the distribution were asymmetric, let's say we were grinding something, the mean, median, and mode wouldn't necessarily be on top of each other. They wouldn't be the same value. In that case, again, the mode is the peak of the distribution, most common value. The median is the 50% point, where 50% of the particles are smaller than this value and 50% are larger. And the mean, again, is the center of gravity. And because the D43 mean emphasizes large particles, it will always be larger than the median and the mode in a situation like this. So there are many other common statistics, and on this slide I talk about the D10, D50, and D90. And here I'm calling them the DV, 0.1. You'll also see the DV10, or just in shorthand, the D10. In this case, we call it V to emphasize that it's a volume distribution. But a lot of times in laser diffraction instruments, the implicit assumption is that the results are being shown on a volume basis, so we drop the V just for clarity, or for ease of use, probably not clarity. So we'll call it the D10. And it has the exact same meaning as the D50, except that instead of 50% of the particles being smaller than, in this case, 10% of the particles are smaller than this diameter. And the D90 is the same thing, where 90% of particles at the D90 micron value are smaller than that diameter. Again, we'll see the D43 somewhere, typically, maybe not in a symmetric distribution like this, but in a skewed distribution. We'll see the mean a little bit on the coarse side of the distribution. And I'll also use this opportunity to talk about the DV1 or D100 and to recommend that you never use it. And that also extends to a certain point to the D99. And the whole idea here is very large values out here, D99, D100, anything where you're looking at the tails of either side of the distribution, the statistics really begin to break down. And I think there's a few more slides on that point a little bit later in the presentation. Let me flip ahead just to make sure. Yeah, there are. So I won't beat that into the ground right now. So let's move on to ways of describing the width of the distribution. So we described 3 different ways, actually 5 different ways of describing points inside the distribution. Now if we were going to be looking at the width, one common one is to look at the standard deviation. There are some industries, some applications where you'd want to look at the geometric standard deviation as well. I know that's very common in the paint and pigment industry. And if you're not familiar with what the standard deviation is, just know that it's a way of moving some certain distance away from a central value. I'm not going to get too in-depth. You know, the Wikipedia page, I'm sure, is excellent at describing standard deviation. Just know that one standard deviation for a Gaussian distribution accounts for 68.27% of the width of the distribution. 2 standard deviations is 95.45, and then it just gets wider and wider as we move more and more standard deviations away from the center. But there are other ways of describing the distribution width. If we were using a dynamic light scattering instrument, we would be talking in terms of polydispersity index, which is also known as PI or PDI. And again, it's just a way of describing some width. We could talk in terms of span. I know there are people that use span in the audience, and that can be defined any number of ways. Traditionally, it's D90 minus D10, all divided by D50, but different users, different industries have custom definitions. So in many different types of laser diffraction software, we can customize how we calculate span. I talked about geometric standard deviation. I know of a few users who also use variance. And then there's actually some homebrew calculations as well, which is why in the LA950 software we added the ability to create custom calculations. So next poll question is whether or not you monitor multiple parameters or not. There's a good deal of users out there who really only monitor a particle size specification on 1 or 2 different parameters. And that's okay, potentially, but I'm always someone who believes more is a little bit better so long as it's rational and makes some sense. So William is saying yes, he monitors D10, D50, D90 plus the mean. That's good. We always recommend whenever you send samples into our lab, either for method development or to evaluate an analyzer, we almost always send out the reports with D10, D50, and D90 as a minimum. And we like that because it gives you an idea of where the central part of your distribution is. It gives you an idea of the fine particles and an idea of the coarse particles. Someone who's monitoring D90, D95, and D99.9. Good, good. So I spend a few slides and a few minutes talking about why that can be, those can be very difficult to monitor. All right. Thanks very much. We'll move on. So to conclude this section, I'd say, be familiar with the nomenclature. If someone's talking about a median, it's important to understand what they mean when they say median. And again, it's hard to avoid sounding like you're making a pun, but try and know what mean means. Right? Which mean are you actually using? And I'd also recommend monitoring multiple parameters if possible. It's always a difficult situation when we encounter users who have specifications only on one parameter, like the D50 or the mean value, and their distribution is just very complex, right? If you were to actually look at the size distribution graph, you might see multiple peaks or just all sorts of interesting information that's very hard to capture in only one parameter. So I'd always recommend looking at multiples. If you can't actually look at the graph, look at multiple parameters wherever possible. And I say that I recommend looking for technical note 156 in the download center on our website. That has a nice explanation of what different parameters actually mean and how you might be able to use them. So now we're going to move on to some guidance from us on how to choose parameters. And these are just recommendations. So choosing good statistics is all about, to HORIBA, it's all about statistics which can describe the distribution in a way that tells us something valuable about our process. The statistics, the parameters have to be relevant. We have to be able to control them well, and they must be reproducible. And it's this last point that I put in a red box to emphasize, because really it's the most important part. If the statistics aren't reproducible, and if they're not telling you anything valuable about either your process or your product quality, then you're just making your life more difficult than it needs to be. And as a general rule of thumb, and it's not always true, but most of the time it is true, poor precision in multiple results is often traced back to either a method that needs some optimization or some statistic choices, some parameter choices that need improving a little bit. And we're always willing to help. So like I said before, you can always contact us at labinfo@horiba.com with any question, and we're willing to dive in and try and help out in any way that we can, because generally happy particle size users tend to make our life easier as well. I mean, not only do you produce better work, but it's better for us. We like to have our users be as educated and informed as possible, and to have as few headaches as possible, because who wants to go to work knowing that you're going to get a headache every day or every week? That's no fun at all. So the next slide, I think the presentation's lagging a bit. Okay, there you go, caught up. The next slide, I talk a little bit about what I refer to as the basis for reliable data. So again, it all starts with reproducibility. You must be able to, whatever you choose to do, get reliable results from multiple measurements. And when I say multiple measurements, I mean prepare the analyzer and the sample, measure the sample, completely empty the analyzer, and then repeat. So that's different than put the sample in the analyzer and click measure 3 times. This is sample in the analyzer, measure, drain, sample in the analyzer, measure, drain. And you do that multiple times. I call that reproducibility. And what constitutes good reproducibility? Well, a lot of times we'll recommend you look at the accepted international standards, whether that's ISO 13320 or USP 429. Not really an international standard, but if you're in Europe or Japan, the corresponding EP and JP documents really are very, very, very similar to the USP 429, which in turn takes its lead from ISO. And here I make the note that if you're not familiar with what COV means, that's the coefficient of variation. It's also known as the relative standard deviation, and I give you an idea of how it's calculated. And these are general guidelines, right? So if you're in pharmaceutical industry, it may be more appropriate for you to look at USP guidelines than the general ISO guidelines, but this is what a bunch of the experts in the industry got together. Instrument manufacturers and users alike got together and said are acceptable reproducibility guidelines. And with the 950 software, we've given some tools to automate how we calculate the coefficient of variation values, so automate the suitability of certain procedures. So in the 950 software, we have an ability to, let's say, pull up the USP 429 guidelines and then give you a green passed or fail So in this case, I don't know how many measurements this are, probably 10 or something like that. It automatically calculates the average for D10, D50, D90, and then calculates the coefficient of variation on each. So it's a nice tool, so you don't have to break out Excel and a spreadsheet and do the manual calculations. And in fact, just this month, Mark Bumiller wrote a technical note, 169, which is in the Download Center right now, which is really just a set of instructions on how to use these features. So if you're interested, I'd recommend going and looking up Technical Note 169. Bill's asking a question about whether or not the coefficient of variation values, I'll go back a few slides, whether they also double when the size drops below 10 microns. It is both for USB and for ISO. It happens with both. All right, so those of you who mentioned that you're monitoring size parameters above D90, these next few slides are aimed at you, and it's not really, I don't want to come off as, I don't want to come off as professorial. I don't mean to lecture anyone, but we've gone through a lot of different method developments where these parameters can be very difficult to reproduce, and we've come across it so often that we decided to talk about it when we discuss sort of general particle size analysis results. So here we go. At a distance of a few standard deviations, non-instrumental errors can dominate. That's really the takeaway for the next several slides. And what it means is when you're looking out here at the tail end of a distribution, maybe at the D99 or even at the D100, or it's also called the D max by some people, the instrument performance really doesn't have a whole heck of a lot to do with how repeatable and reproducible those statistics are. And that's what we mean by non-instrumental errors. It's really statistical errors because the number of large particles out here on the edge are so small compared to the number of particles out here in the body of the distribution that if your measurement length is too short, you may not see them in every possible scan, which means that the D99 value is going to flicker potentially from one measurement to the next. It also means that there's very few levers we can push to improve the precision of these values. Really, measurement length is one of the only ones, which is very different than the body of the distribution. There's an awful lot of things we can do to help precision over here. Very few things we can do over here. So again, when we're talking 2 or 3 standard deviations away from the mean, you're talking about so few particles it becomes very difficult. And what we always tell people is that if you want the same level of reproducibility at the D99 value as, let's say, the D50, the challenge is really about analyzing similar amounts of material in the D99 area. And we know that that's not the case, right? We know that there may only be a relative handful of particles, a handful of your largest particles compared to the number of particles at the D50 value. And one of the key challenges here that I haven't talked about yet is sampling and dispersion. Right? Those are the two things that you need to take care of as the user before the sample even hits the analyzer. And let's say you're starting from a powder and you're trying to reproducibly sample your largest particles. Chances are good that's going to be very difficult if you're not very careful about your sampling technique. Either using a spinning riffler or a shoot riffler or some technique that's not necessarily just scooping into a bottle. Very difficult to reproduce your largest particles because, let's say you're just taking a spatula and digging into a bottle. The largest particles are probably the most likely to roll off the edge of the spatula, or maybe the bottle itself has sort of separated into different layers of different particle sizes because it's been shaken a lot. And then when you get to dispersion too, if it's a big chunk of smaller particles, we'd call those agglomerates. they may disperse much more slowly than smaller chunks, simply because the amount of surface area available is much smaller. The surface area to volume ratio, I should say, is much smaller. So those are, there's just an awful lot of challenges when you spec out on the edge like that. Now, that said, there are some applications where having any large particles is the most important thing you want to get out of a particle size analyzer, and we're definitely very understanding of that. I just want to draw some extra attention and some extra concern to this. Measuring the D99 is not the same and not as easy as measuring the D50. And typically what we recommend to people, instead of looking at D95, D99, etc., is to try and specify the percentage of material greater than a certain size. And another way to think about this is, what information is the D99 going to be telling you? It's going to be giving you a size, right? Let's say that size is 4 microns. Now, is it really important that the D99 is 4 microns? Or is it really important to know that there are no particles or very few particles above a certain size? Most of the time, it has to do with the actual size. So I can think of a few applications where they just don't want anything larger than a micron, right? And instead of saying, the D100 or the D99 must be between this and this, it could be valuable to say instead, we just want to measure what percentage of the distribution is greater than 1 micron, because that's really what we're interested in. And that could be a lot more reproducible than monitoring the D99. Or another way of thinking about that is, instead of being more reproducible, it just has less fluctuation, so less headaches on your end. So, quick poll, and I'm just kind of generally curious, do you have a specification that's difficult for you to meet? And if it is difficult for you to meet, does it relate very strongly to product or process quality? And I would imagine a lot of people in the audience today may be needing to satisfy product specifications that maybe weren't set when you were with the company or when you were in the room. We've certainly run into that situation a lot as well, where the specification may be 10 or 15 years old and may not have involved a lot of the current best practices, things like that. Yeah, so I'm getting a response from a few of you that you do have a spec that's difficult to meet, that causes some headaches. And I would definitely recommend you send an email either to me or to labinfo@horiba.com just to see if there's anything we could recommend that might make your life easier. It's always worth it. It's always worth asking. Can't hurt to ask. Thankfully, there's not too many people that are saying that the specs that you have to measure do not relate to product or process quality. That's good. Those are the worst scenarios, where not only is it difficult, but it doesn't really have any value, so you're sort of banging your head against the wall for no reason. All right, thanks very much. So some conclusions for this section. The parameters and statistics that you choose should ideally reflect product performance or process performance, and don't need to make your life any more difficult. I'd recommend looking at webinar TR007 called Setting Size Specifications, and Technical Note 161, which has the same title, in our Download Center. Both of those cover a lot more information in depth about how to choose rational size specifications that make a lot of sense and maybe aren't so very difficult. I'd also recommend, when in doubt, look to the appropriate standards. That could be ISO 13320 in most cases. If you're in pharma, you'd be looking at USP 429 or the equivalent EP and JP. And again, as a recommendation, avoid monitoring the extremes whenever possible. If you really care about large particles, maybe the mean is enough. Just tracking small changes in the mean can give you an idea of large particles. And it's a lot more reproducible than, say, the D99. So now we'll go into some result interpretation case studies. So one very common one is when your sample has multiple modes. And in this case, we always recommend using a feature in the LA950 software, and it's a feature I'm sure in a lot of other instrument software as well, called the multi-mode report. And why we recommend the multi-mode report is because if you just apply the general D10, D50, D90 parameters to a multimodal distribution, you'll get something that doesn't make a whole heck of a lot of sense. Your D50 is going to be somewhere on the coarse end of your fine peak. Your D90 is going to be, it's just not going to be very rational a lot of times. You could come up with a specification that's easy to meet, but a lot of times it's going to be more difficult than if you spec'd on each peak individually. And that's what the multi-mode report can do, is it'll look at your distribution, and it's actually a smart splitting of the two peaks. So in this case, it's extrapolating the sizes instead of just sort of drawing a hard line right down the center of where the two peaks meet. It's extrapolating the size distributions on either end, and it's giving you D10, D50, D90 values, also mean values, mode, a bunch of different things for each individual distribution. And that's a lot more reliable and easy to spec on than, say, D10, D50, D90 for the whole distribution. Another common pitfall is something called multiple scattering. And that's where the light in your laser diffraction instrument is scattering off of multiple particles before it hits the detectors. And that's bad because every time the light scatters off of a particle, the angle of scatter increases, and that's interpreted by the algorithm, based on scattering theory, it's interpreted to mean that the particles are smaller than they really are. So a wider angle of scatter always means smaller particles. So we always want to avoid multiple scattering, and a telltale sign that multiple scattering is beginning is the appearance of a small peak that was never there before. So in this case, I ran this experiment myself a few years back. We took some particle size standards manufactured by a company called White House Scientific. This, I believe, is PS202. And I just started adding bottles. So when you buy a pack of PS202, it comes in a box of 10 bottles. All the bottles are supposed to be single shots, so you dump the whole thing in. When I dumped one bottle in, I got passing values on D10, D50, D90. That's what verification 1, 2, and 3 mean. Passing values compared to the certificate of analysis. When I dumped 2 bottles in, I increased the concentration of particles in the system. And that's what transmittance means here. So as the transmittance values drop, it means that the amount of scattered light is increasing, and the concentration of particles in the system is also increasing. So 2 bottles, I'm scattering more light, but I'm still passing D10, D50, D90, that's okay. But at 3 bottles, I'm now at 58% transmittance, which is really very low for anything except very strongly absorbing materials. And in this case, they're glass beads, so there's no absorption, they're not opaque. And all of a sudden, I'm no longer passing on my D10 value. So it gets an NG value. D50 and D90 are still okay, though. And as I keep adding more bottles, essentially what we see is the formation of this small peak, which was never there before, and the whole distribution values for D10, D50, D90 are being pulled out of spec. All right, and again, we don't usually like to spec D10, D50, D90 in a multimodal distribution because the D50 is just statistically being pulled finer here. Nonetheless, this is a telltale sign. Anytime you add more and more particles and you see a finer peak appear, that's a clear indicator that multiple scattering is beginning. And it should be a reversible process. So if you were able to dilute the sample back into a good scattering region, you'd see the peak disappear. If it didn't disappear, then it's probably real particles that somehow are forming. Maybe the sample is dissolving and then recrystallizing at a much smaller size because it's maybe more thermodynamically stable at the smaller size. And if we could extract the scattering patterns, the light scattering patterns for all 10 bottles, we'd see another trend taking place, which is that more and more light is being scattered to the wide-angle detectors. And in the LA950, wide-angle detectors are the larger numbers. So as we go from detector 45 to 75, the angle of scatter is increasing from, I don't know the exact angle, but let's say in general from 0 to 180 degrees. And what we see here is that the 9th and 10th bottles are the sort of teal and very light sky blue, and they are scattering much more light on these wide-angle, high-number detectors than 1 and 2 bottles. This fits the expectation, so it's another clear indicator that we're starting multiple scattering. You don't necessarily need to take it to this extreme, but a lot of cases aren't necessarily as clear-cut as this one is, in which case it could be useful to look at a tool in the 950 software called the intensity graph, and just see if the light scattering on your wide-angle detectors is monotonically increasing. All right, another common challenge is how do you disperse agglomerates? So here the case study was dispersing dry powders using the powder jet accessory. And I forget the exact sample, but it definitely had some coarse agglomerates in there. Right? So one of the levers we can change, one of the factors we can change in dry measurement is air dispersion pressure. So we changed it. We measured first at 1 bar, then at 2 bar pressure, and we get the middle graph here, and then finally at 3 bar pressure. And then now we get these 3 different results, and you want to know which is the most accurate result, or maybe the most well-dispersed result. And it seems fairly clear that the 3 bar result is probably the best dispersed. And the reason I say that is because as we increase the dispersion energy, the coarsest particles disappeared. Or they didn't really disappear, they were sort of distributed to the rest of the distribution. Right? So the small particles, your medium-sized particles, are all combining to form these large agglomerates out here. They're not likely to be large particles, actual large single particles, because they're disappearing as we increase the dispersion energy. Right? If this graph remained where it was at 1 bar, 2 bar, and 3 bar, then that's a very good bet that those are actual large particles. Now the flip side is, as we increase dispersion power, we run the risk of starting to break some particles. If you kind of imagine measuring a pencil, right, a very, very small pencil, if you hit it with enough energy along the length of the pencil, you're going to maybe break it in half, or you're going to break it somewhere along the length of the pencil. And now instead of 1 whole particle, you have 2 much smaller particles. And where we always see breaking particles in the distribution is right on the fine side here. We'll see a corresponding decrease in the coarsest particles, but then all of a sudden we'll see the fine side start to stretch out. And that always means that you're breaking particles, right? And it's not necessarily a bad thing, because it could be that, you know, depending on what you know about your sample, it could be that these are agglomerates, and this is just the trade-off you need to make. To get to your best dispersed state, a lot of times you don't have the luxury of choosing between full dispersion and no breaking. A lot of times these processes happen in tandem. But if you know your particle to be very easily friable, then this is something you want to be on the lookout for. And this is kind of a subtle case. A lot of times we'll see an actual distribution appear at very small sizes. So those are just some easy examples, but very common examples as well. And so some conclusions from this section. I would always recommend look at the distribution graph whenever possible. And it's not always possible, because I know our specifications 99.9% of the time don't say look at the distribution graph. A lot of times we just have maybe a D50 value that we need to hit, or a mean value that we need to hit, but you're kind of missing the forest for the trees. So I would always recommend look at the distribution graph. There's always going to be something interesting on there. Let's say that you could be hitting your particle size specification dead on, but for whatever reason your process has just been performing terribly over the last several weeks. It could be something new that's appeared in the distribution graph that maybe isn't showing up in the specs or in the parameters you've chosen for the specs. So always look at it. And just remember that precision's not the same thing as accuracy. As you vary measurement and calculation parameters like dispersion pressure, a lot of times we do those things to improve accuracy, right? In the dry case studies I just went over, it's to get closer to the most well-dispersed primary particle state. But but that shouldn't be the first goal. The first goal should always be have a method that's reproducible. Precision's always better than accuracy. Or I should say precision is always the first step before we worry about accuracy. And so that's the presentation. The last slide here just has a few links. For more information, we've got new documents every month up on the website, new webinar announcements all the time. Go to horiba.com/us/particle. You can always contact us directly at labinfo@horiba.com. I will type in my email address into the chat box again, just so that you have it. And you can go directly, we call it the Download Center on the website. That's where we put all of our documents. And it does require registration, but it's relatively painless. We don't ask for any personal information, just professional information. And lots of good webinars there, lots of good technical notes, some application notes, a lot of good stuff. So that was the presentation. If you have any questions that you haven't asked already, go ahead and send them into the chat box now, and I'll spend the next few minutes answering them. All right. So I apologize in advance if I mispronounce some of your names. I know from experience, having the name Trevor Honest, that it's not always easy to pronounce these things. But Feng Shao is asking, how can we change the air pressure? And so if you have the LA950 powder jet accessory, or really it could be any manufacturer's instrument, any dry powder accessory, there should always be a, it used to be a hardware dial, a long time ago. Now it all should be controlled by software. I know in the case of the LA950 software, it's just an up and down arrow where you can specify anywhere between no pressure, so 0 bars, and 4 bars pressure. And it's adjustable in 0.1 increments, so 0, 0.1, all the way up to 4.0. And by no means would I recommend doing a pressure study for 40 levels, because you're probably not going to get very, it's going to definitely be diminishing returns, but it's always good to test with 3 different pressures, something that's small, medium, and high, let's say. Bill's reminding me that sampling errors can be a major factor compared to instrument errors. Thanks, Bill. All right, I'm going through past questions that have been sent in. There's a question about, effectively, how much does this person have to worry if their particle is very strongly needle-shaped, has a very high aspect ratio? And it depends. I know that sounds like a cop-out answer, but it's also an honest answer. A lot of times, let's say you have a needle that has an aspect ratio of 5:1. A lot of times it's going to appear as a very wide distribution in terms of equivalent spherical diameter, because the needle is going to be spinning a lot of times. Depending on the flow rate and what you're doing with the analyzer, chances are good that the particle is not going to be perfectly aligned as it passes through the laser beam. So it's going to be spinning in all sorts of different orientations, and based on the shape of the particle, some orientations are going to be more likely than others. Or, a different way to say that is, it's much less likely that the needle is going to be seen, head-on, sort of, like from the narrow end only by the laser beam than in some other much longer projection. So you're going to get a very wide distribution. Sometimes we've seen people come up with a bimodal distribution where you have a very narrow, small peak and a very wide, larger peak. And in that case, it actually is reporting the sort of head-on distributions. So in that case, the particle's tumbling slowly enough where the laser is able to see, or I shouldn't say that it's tumbling slowly enough, it's tumbling in such a way that the laser can see the head-on projection and report it as a separate distribution. And so that's kind of neat, actually, because the head-on projection gives you an idea of what the width of the particle is, assuming that in this case, the needle can be described by the length and width, and the depth isn't any different than the width. But that's actually kind of neat because it gives you an idea of what the width of the needle is with a high degree of accuracy, because again, chances are the width, as you look at the head-on projection, is much closer to being a circle or a sphere than the length projections are. And so that's much higher accuracy than the much wider, larger distribution, which is all the different length projections sort of combined together. But again, whatever error you get in terms of accuracy, a lot of times isn't so significant for people because it still allows them to see changes in product quality and process performance. So let's say you purposely want to create a needle with an aspect ratio of 5:1. If for whatever reason your process changes, so now you're creating needles with an aspect ratio of 3:1, you're still going to see that change in the data. The distribution is still going to get smaller. So in that sense, laser diffraction is a perfectly usable technique and valuable technique, and in a lot of cases will be faster and a little bit easier to use than other technologies which will actually image the particle. All right. Feng Xiao asks another question. For multimodal peaks, how do we calculate aspect ratio? Report has a peak 1:2 aspect ratio. How is it calculated? It's really just I believe it's just a ratio of two different key parameters. It's not a true aspect ratio. It would be a true aspect ratio in the situation I just described, where it's a needle. Then you can think of it as the actual particle aspect ratio. Otherwise, it's just going to be the ratio of two different parameters for the two different peaks. It may be the mode, it may be the median. I forget which off the top of my head. Bill is saying it's the ratio of the two modes. I'll take your word for it, Bill. I'll have to check after the presentation, but it's really not the aspect ratio. It's really just more of like a volume percentage. Manish is asking, how do you control the transmittance? Well, you control the transmittance by adding different amounts of sample. So a lot of times, one of the more common method development tweaks that we make for users is if they have a very highly concentrated starting material, or if it's a powder and they're predispersing it into something, a lot of times we'll dilute it a little bit further down so that when you're adding material to the analyzer, one drop here or there isn't going to wildly swing the transmittance. So that's the advantage of having a little bit more dilute sample, so long as you're not changing the sample stability when you dilute it and all that. But the more dilute it is, the more fine control you have over how many particulates are being added into the system and what effect it's having on the transmittance. And ideally, a lot of samples will have some range of transmittance values where you have enough scattering going on to activate all the relevant detectors at all the angles where you're going to get good size information without adding so many particles that you start getting into multiple scattering. And that's sort of a drawback of adding very concentrated sample into the analyzer, is one drop could take you all the way down to 60% transmittance. In that case, you have to use the analyzer, the auto-dilution controls maybe, to auto-dilute it back up to a good transmittance range. And this all assumes that there's no absorbance in the sample. If I was going to be running carbon black, something that naturally is going to absorb any light that goes to it, or a large amount of any light, then I will need to aim for a lower transmittance value. In that case, 70% transmittance, 60% transmittance, even further, could be acceptable, could be appropriate, because a lot of the light that is interacting with that particle is being absorbed instead of being scattered like a non-absorbing particle. Another question just came in. What about the percent residual of analysis? Okay, so I think I know what you're getting at, Alvaro, with that question. Different manufacturers call it different things. One manufacturer, not HORIBA, refers to something called the residual. We call it the R parameter. I'm sure it's just just a difference in marketing terminology. What we mean when we say R parameter is how it's basically a goodness of fit measure. And what I mean by that is what the analyzer is actually doing is it's just collecting a scattered light distribution. It's just a pattern, intensity and angle of scattered light. And that information gets passed to an algorithm in the software that takes that information and gets some particle size distribution out of it. Now, there's a few different factors that go into what particle size distribution comes out of that scattered light. One of the factors is refractive index. Another factor is how many times do we run the scattered light pattern through the algorithm in an iterative manner. And both of those things affect how well the derived particle size distribution fits the original measured scattered light pattern. And typically we like the residual or the R parameter to be smaller. We like it to head in a closer to zero direction because that way we know that the fit is improving. Now, there's a danger in only trying to minimize the residual or R parameter because you could also be fitting noise that's in the measurement, and every instrument has noise. Some instruments have much less noise than others, but it's unavoidable, right? Unless we were to construct the analyzer out of perfectly absorbing materials, there's always going to be some stray light in the sample chamber, and that's always going to be recorded in the measurement. And we can't blank all of that out before we add the particles because the particles themselves, the scattered light off the particles, is going to be adding to the stray light as well off of different surfaces in the analyzer. So a lot of times we don't like necessarily to focus on minimizing the residual at all other costs because you're going to start fitting noise, and that's going to give you some spurious peaks. And then that's going to be just as misleading as if you had a higher residual. So, but that's what it means. We have a document on the website. Another technical note that the exact technical number escapes me. I think it may be 153, TN153, and I'll put that in the chat box. I think, and that's understanding how to use chi-squared and R parameter values, or something like that. But it's in the technical notes section of the Download Center. I'd say definitely download that and read it, and hopefully that answers your question a little bit better than I can. If not, email us. Manish is asking, if you don't know the refractive index of the particular sample, what refractive index should we use? Very good question, very common question. Refractive index is probably one of the areas that most laser diffraction users feel most uncomfortable about because a lot of times your company or your research group or university are manufacturing novel particles where you can't just turn to the CRC handbook or the manufacturer of the particle for information about what the refractive index is. So, and we run into it an awful lot in our applications lab here. A lot of times we'll get particles where the user either doesn't know the refractive index or for reasons of trade secrets doesn't want to reveal what the particle is, different things like that. A lot of times we'll just start off with a general value of 1.60 for the real part of the refractive index. I'll type that into the chat box as well. 1.60 is a good starting point. It's reasonable for 50+% of materials. And then you want to know a little bit something about the material because the next thing we want to specify is the imaginary component of the refractive index, and that has a lot to do with how strongly the particle is going to absorb light, what shape the particle is, how much it might reflect light. So if you're measuring a transparent particle that's a sphere, like a glass bead, or a polymer, let's say, non-absorbing polymer, the imaginary index is going to be 0.0. That's kind of a nice trivial case. If you're measuring something like carbon black, the imaginary index is going to be greater than 1.0. And really, without getting too far into it, because it's a great question and there's a lot of information that would be valuable for you, I think, I would say, again, we have a lot of information on the website. I would recommend TR003 webinar, TR003, and that has everything to do with choosing a refractive index for laser diffraction. And we have, I think, at least 1 or 2 or 3 technical notes on the subject. In fact, we just created a new web page about it. All sorts of different things. If you want to send me an email, Manish, I can give you links directly to all that stuff so you don't have to find it on your own. All right, well, I think it's probably a good time for me to end the webinar. Again, I have to apologize for running a little bit late. I'm glad we got it going, though. I would have hated to reschedule, and I don't know how to prevent the same thing from happening next time, but better to focus on good things happening than preventing bad things from happening, I suppose. Anyway, thanks everyone for showing up. I hope you learned something useful. I hope it was valuable for you. When you leave the presentation, you'll be presented with an option to take a short survey. If you have, 4 or 5 minutes, please do take the survey. It does give us some valuable feedback, very valuable feedback about what you liked about the presentation, what you didn't like, ideas you might like to see in the future. I do look at every single survey. In fact, several people look at every single survey, so your opinion does matter. Otherwise, I hope you all have a great rest of the day, and thanks again for attending. Bye, everyone.